Good morning, students. Once again, welcome back. Here I am just going to discuss of your class 11 mathematics. Okay, which you are looking forward with eagerness and interest. Yes, uh, which is the most vital chapter. I am going to discuss chapter 1 set theory. Okay, here I am going to discuss the introduction of the set theory. And yes, students, class 11 mathematics, you are all going to class 11 after your class 10. You have done fantastic in your exam and you are looking forward, okay, to class 11. And your students, class 11 math is the most vital mathematics which laid the foundation to class 12 math. Relation and function are most vital chapter to calculus, and without which the calculus is never understood. The calculation is the study of the derivative and integration and their practical application in various fields of mathematics and science, mostly physics, okay, and engineering. So without calculus, you can't understand. It is difficult to understand. Similarly, set theory is the most vital chapter which gives the clear understanding and idea about the relation and function, without which the relation and function is never understood. So you have to take importance of these chapters, and it has wide application set theory, okay, and various application and importance and significance in solving the various problems, besides giving the idea about the relation and function. Okay, so here I am discussing the introduction set theory. The basic concept I am going to explain, and also I have discussed the Adisama solution of exercise, first chapter, first exercise, okay, based on the concept of the set theory which I am going to discuss here. So I hope you will understand and you will go through the class and you will understand the concept. The class has been vividly explained, lucidly explained for you, okay. Take interest of the class. Yes, set theory is the first chapters of your class 11 which I am going to discuss here. And set theory has many applications and significance in our practical life. It is widely applicable in our everyday life. Mathematics in our everyday life, okay. Without the knowledge of set theory, it is very difficult to understand. Look at an interesting question here. In a school, all pupils play either hockey or football or both. 400 play football, 150 play hockey, and 130 play both the games. Find the number of people who play football only, the number of people who play hockey only, the total number of people in the school. An interesting problem. Only can be solved with the help of the set theory, with the knowledge of the set theory. Similarly, set theory has many applications in everyday life. Here is another question, interesting question, vital questions. Such kind of questions only can be solved with the help of the knowledge of set theory. So, it has significance, it has importance, okay. So, you have to take care of these chapters with utmost attention. Set theory in everyday mathematics. Here is another question. See how interesting the question is. Logical question, vital questions, and this kind of question only possible through the knowledge of set theory. So the set theory has wide application, set theory and set operation, right? Okay. So this set theory, who is the founder of set theory? This set theory, again you see the set theory in everyday life. You see the problem is there. Such an interesting and amazing problem for you, okay, and which can be solved with the help of the set theory. So who is the founder of set theory? Who is the creator of set theory? Who is the initiator of set theory? George Ferdinand Ludwig Philipp Cantor was born March 3, 1845, St. Petersburg, Russia. Died January 6, 1918, LA, Germany. Was a German mathematician, was the founder of set theory. So George Cantor was popularly known as the founder of set theory. George Cantor was the founder of set theory, was the initiator of set theory. The concept of set theory was initiated by George Cantor. So what do we mean by set? Define set. Set is nothing, is a collection. A set is a collection of well-defined elements. What is set? Set is a collection of well-defined elements or object or members. Okay. For example, the set of geometry box. If you say the geometry box, it is useful in different geometrical activities. The elements must be well defined. These are the elements, members, or the object of the geometry box. The collection of objects. So set is a collection of objects. Okay. Hence, the scale belongs to geometry box. The objects are well defined, belongs to the symbols transfer, belongs to, or scale is an element of the set theory. Geometry box. I will discuss the symbol belongs to. The belongs to means is an element. Mathematical notation, set notation. Okay. Scale belongs to set of geometry box. Compass belongs to set of geometry box. Eraser belongs to set of geometry box. But the spoon does not belong to geometry box because during the geometrical construction and activity, the spoon is not required, and the spoon is not the element which is not required, okay, for any geometrical activities. The element is not well defined. So the elements spoon is not well defined for geometry box. This is understood that the element of a set must be well defined, and set is a collection of well defined elements. Once again, see, the compass belongs to geometry box, is required, inevitable, essential for any geometrical activities and construction. Yes, so the compass is an element, and the element of a set is well defined. Similarly, the protractor belongs to geometry box, and also, okay, for geometrical activities, for construction of angles and different kind of geometrical process and activities. Element of the set is well defined. The protractor is required, without which the measurement of angle is not possible. Scale belongs to set of geometry box. Is required, without to draw a line or perfect measurement, accurate measurement, without which we cannot draw a line segment and geometrical construction. So the element of set is well defined. But spoon does not belong to geometry box, set of geometry box, because it is not required to construct any kind of construction. Spoon is not required to any kind of geometrical construction. So it is clearly understood that, observe that, element of a set is well defined, and set is a collection of well defined elements. How to represent a set? A set is usually represented by the capital letter of English alphabet, such as capital A, capital B, capital C, capital D, etc. Elements of set are represented by small letters of English alphabet, such as small a, small b, small c, small d, etc. Also, element can be expressed with the help of the numbers and different kind of symbols. Beside this, if A is an element of the set A, we can write as notation A belongs to A, read as A belongs to A. Understand? Okay? So, this is known as A belongs to A, the geometrical notation. Understand? Similarly, if B is not an element of the set A, is not an element of the set A, we can write, how can we write? The B does not belong to A. The B does not belong to A. And we can write it, we say B does not belong to A. This is the geometrical notation, belongs to, if an element belongs to the set, we can write, is an element of the set A, we can write, you can write it as a notation, set notation belongs to and does not belong to. Okay? Representation of set in set theory. There are different set notation used for the set theory to represent a set. Okay? So mostly there are three set notation we can use to represent the sets. First of all, semantic notation, semantic form, rooster method, rooster form, bias, mathematics and rooster, and the set builder form, property method. Okay, the three methods we can use to represent this, to notice, to represent the set. Okay, here the semantic form. The semantic form is a set of past 5 natural numbers. A set of past 5 natural numbers. So here the set can be expressed in the form of statement. In the form of statement. This is known as what? Semantic form. A set which can be expressed in the form of statement is known as semantic form. And here the elements written distinctly, clearly, every element, all elements are written, including separated by comma and enclosed by curly brackets. This is known as rooster form. In rooster form, all the elements are written clearly, distinctly, okay, understand, by comma, and all the elements should be enclosed by the curly bracket. And builder form, this is the rooster form, and builder form. In this form, the set, this is the symbolic expression of the set. And this is the property method of the set. And every element has a common property. Using this property, okay, we can express a set that is known as the set builder form. Okay, so there are three forms. One is the semantic form in the form of statement, rooster form, writing the elements vividly, distinctly, clearly, and using the property method that is known as the set builder form. Let me discuss one by one here. What is semantic form? Yes, the semantic form is it is a notation of the set which can be described in the form of statement. A set which can be described in the form of statement is called semantic form. For example, a set of past 5 odd natural numbers in the form of statement is a semantic form. A set of natural numbers, okay, in the form of statement is the semantic form of the set. And a set of whole numbers, semantic form of the statement, in the form of statement. So, a set can be described, can be written in the form of statement is called semantic form. Clear? This is one of the way we can write, we can represent a set. The another method is known as similarly a set of integers also in the form of statement, semantic form. Okay? The another form is known as the rooster form, rooster method to represent the set. And in this set, every element, all the elements of the set should be written clearly, distinctly, separated by comma, and all the elements should be enclosed by curly bracket and separated by comma. For example, the set B. You see what kind of elements are there? Here you see 2, 4, 6, 8 and 10. These are the 5 even natural numbers, which is a collection of first 5 even natural numbers. So here it is in the form of which form? Rooster method. In the rooster form, all elements we have to write every element of the set clearly and distinctly. In rooster form, the order of the element does not matter. The order of the set does not matter. We can write the element of set in any order, and the set will never change. The set remains same. For example, the first 5 even natural number also can be written. We can write here, we can write 2 here, here it is written in systematic order. So order is not required while you are writing the element of the set. Here 6, 8, 10 and 4. You see, it's not in proper order. You can write the element of any order. Suppose geometry works, the elements you can keep the geometry works inside the geometry works elements or say the geometrical instrument in any order, but the elements are remain same. These are well defined. Also, if there is an endless list of elements in a set, so a set has infinite number of elements. Okay, so they are defined using a series of dots at the end of the last element. Look at here. For example, the infinite set is represented set of natural number. You write 1, 2, 3, 4, 5. Again, dot sign are given at the end of the element 5. It shows that the set has infinite number of elements. It means it contains infinite number of elements and which we cannot count. How many elements of the set n we can count? And it's an infinite set. In this cases, we can express the infinite set by at the end of the elements by dot sign, by giving the dot mark. The example of sets in the roster form, look at here. The set of all natural numbers and n is equal to what? You see here 1, 2, 3 given by curly brackets. This is an example of set of roster form. The set of whole numbers capital W, which is 0, 1, 2, 3 dot, which is an infinite set. Set of integers capital Z is also an infinite set. And these are the elements are written in the roster form. In this form, the elements are written clearly, precisely, distinctly, and all the elements must be enclosed by a curly bracket. And every element is named by capital letters of English alphabet. Okay? And another form is known as the set builder forms. And in this set, every element, all the element has a certain property and rule. The set builder notation has a certain rule or a statement that has a common characteristic property. That is a common characteristics property, features. All the elements have a common property. So in these cases, we should not write all the elements clearly, and all the elements written in a single with the help of single variable. Okay? Understand? And which stands for all the elements of the given set. And the set builder form uses a vertical bar line or semicolon in its representation with the text describing the characteristics of the elements of the set in the builder form. For example, the set A is x such that the symbol vertical bar line is known as such that yes, x is an even number, x is less than equal to 20. It means the bar sign at the right side of the bar sign is represent the what properties of the set, what kind of element should a set contain. Here x is an even number, elements should be even number, and x is less than equal to 20. It means the element are equal to 20, all the even numbers equal to 20 or less than 20. The statement says that all the elements of the set A are even natural numbers that are less than 20 or equal to 20. Okay? And before the bar sign, here it is in what? The element. This is the element x with the help of the single variable, and what kind of element it should be on the right side of the vertical bar. This is the property and this is the element with the help of single variable, with the help of the set builder forms. Sometimes we can use the semicolon instead of vertical bar line, and which read as such that the symbol is known as such that this vertical line is known as such that we read as A is equal to the set A is equal to x such that x is an even number, x less than equal to 20, x that such that. Okay, the semicolon and the vertical bar is known as such that. We read it. How to read the set? Very important. Example of set builder form. The set of all natural numbers in the builder form, which is capital N, is equal to, written here you see x such that x belongs to n. The set of all numbers capital W is equal to x such that, here semicolon we can use, x belongs to W. The set of integers similarly capital Z is equal to x such that x belongs to Z. Okay, so these are the basic concept of the set theory, intro to set theory. Here is an assignment for you. Okay, you try for the assignment here. Okay, and I have explained exercise 1.1 of your addition or solution, and you take toward the class, and also I am going to prepare the similar kind of class for you, the concept of important concept of set theory, and we will explain how the set theory is applicable, and different and set operation was the most important factor. Okay, understand? Next class I will discuss what is the different types of set. Okay, understand? So go through the class. Once again, thank you for interest and eagerness for the class.
Once again, welcome back with another interesting and vital class which I am going to discuss of your class 11 mathematics. Okay, chapter 1 set theory. Okay, and in this class I am going to discuss the types of sets. Okay, and this is the second part of my class set theory. Okay, and which I am going to discuss. In the first part already and it has been discussed the introduction set theory and what do we mean by set, and what are the different notation of the set, how to represent the set, and also you have done exercise 1.1 of your Addisama math book, right? And this is a class where you will get all the basic concept of the set theory. This is the second part of the class. Okay, understand? So I hope you will take interest and eagerness toward the class till the last moment of the class. You will watch it, and it is a kind of point of learning. You will get every details, okay, of the basic concept of the set theory, that is the types of set. Okay, so in this class I am going to discuss types of set, and in the following points I am going to discuss these are the different kind of sets. First of all is the cardinal number of sets, singleton set, finite set, infinite set, empty set or null sets or void set, non-empty sets, subset and superset, proper subset, equal set, unequal sets, right? Equivalent sets, this is another important concept over the set theory. Overlapping sets, disjoint sets, universal sets, and power set. So these are the most fundamental concept of the set theory which cover entire part of the set. Okay, basic concept, types of set, which I am going to discuss. Okay, and along with the suitable examples, Venn diagrams. Okay, understand? Let's see. Let us see the first point and the cardinal number of set. What is cardinal number of set? Okay, the first point, basic concept, definition of cardinal number of set. It is saying the total number of elements in the given set is known as cardinality of the set. Okay, the total number of elements in the given set is called cardinality of the set, right? The cardinality of the set A is denoted by n of A. Suppose for example, the set A contains the element 2, 3, 5, 7, 11. So the cardinality of the set A, the total number of element of the set A is equal to n of A is 5. Very simple concept. So how many elements a set contains is known as cardinality of the set. The cardinal number of set or cardinality of the set, right? Another example, suppose the set B contains A, B, C, D, E, F, G. So how many elements are there? Yes, 1, 2, 3, 4, 5, 6, 7. Very simple. So the cardinality of the set B is n of B is 7. Right? Second point, the singleton set. A set that has only one element is called singleton set or also called a unit set. Set having only one element. Example, the set A, x such that x is an integer between 7 and 9. So what is the integer between 7 and 9? If you write in the builder method, the element will be 8. So it has only how many element? One element. So this is called a singleton set. Since the set A having only one element. Similarly, the set B, x such that x is a natural number and x is less than 2. What is the natural number less than 2? If you write in the roster methods, it will write and the set B is equal to one element. The element is 1. So the set B has only one element. So both the set are singleton set because the set B has only one element, the set A has only one element. Very simple concept. Okay. Next point, finite set. So what is finite set? A set having countable or finite number of elements is called finite set. It means if you are able to count how many elements a set has, then such type of set is said to be finite set. The cardinality of the finite set can be determined because we can say how many elements the set has, the finite set has. So if the number of elements of a set can be determined, then such type of set is said to be a finite set. For example, the set C in the builder form written x such that x is a prime number less than 25. So if you write in the rooster methods, then the elements are, you can clearly see the elements, how many elements are there. And you can find out how many elements? There are 9 elements. Because the cardinality of the set C, NC is equal to 9, and we are able to find out the number of elements of the set C. So the set C is a finite set. It has 9 elements. So the set C is a finite set. Infinite set. Okay? A set with an infinite number of elements. And we cannot find out how many elements the set has. The cardinality of the set cannot be determined. For example, the set D, x such that x is a natural number. What are the natural number? If write in the builder method, in the rooster method, you see the elements are 1, 2, 3, 4, etc. So clearly this is an infinite set because you cannot find out how many elements the set has. Because the dot sign shows the set is a what? Infinite set. The cardinality of the set cannot be determined. The set D is an infinite set because it has infinite number of elements and the cardinality of the set cannot be determined. Right? Another example of infinite set, the set N 1, 2, 3, 4 dot is an infinite set. Here set of integer, okay, is an infinite set. Here another set V, you see, is also infinite set. Because we cannot determine, we cannot find the number of elements of the set. They have infinite number of elements. The elements are uncountable. We cannot count. If we can count, during the process of counting, the counting process will never to an end. The counting process will never end. We cannot say how many elements the set has. And the cardinality of the set cannot be determined. Okay, students, right? Here is another set X, set C, X such that X is an integer, is an infinite set. Next point, empty set or null set or void set. What is empty set? Very important point, empty set. A set that does not contain any element is called an empty set or null set. An empty set is denoted using the symbol phi. It is also read as phi. Cardinality of the null set n of phi is equal to 0. And you can write the set M is equal to phi, okay, and which is a null set. The set X, Y says that Y belongs to N, Y is greater than Y. Is it possible? A natural number is greater than itself? It is never possible. It means the set X does not have any element, so this is an example of null set, phi set. Right? Non-empty set. A set having one or more than one element is called a non-empty set. For example, the set A is equal to X such that X belongs to N, X is less than 2 is a non-empty set because it has one element. Another set V is equal to Y such that Y square minus 1 is equal to 0. If you solve Y square minus 1 is equal to 0 and you can convert the set into from builder method to rooster methods, the element will be 1 minus 1 is a non-empty set. Okay? The cardinality of non-empty set is never 0 because it has at least contain one or more than one element. Right? Subset and superset. Very important concept about the set theory, subset and superset. It has been explained so vividly. Okay? So look at here, for two sets A and B, if every element of set A is present in the set B, then the set A is a subset of set B. If A is a subset of B, then it can be written as A subset of B. If A is a subset of B, then we say B is a superset of A and is written as B is a superset of A. And this is the symbol of subset, and this is the symbol for superset. Consider the set A is equal to 1, 2, 3. Another set B is equal to 1, 2, 3, 4, 5, 6. Here you see clearly A is a subset of B. Here A is a subset of B means all the elements of the set A are present in the set B. Right? Understand? Since all the elements of the set A are in the set B, so A is a superset of B. And since all the elements are contained in B, the set B, so B is the superset of A. So here B the superset of A denotes that B is the superset of A. So consider the set A is equal to 1, 2, 3. Another set B is equal to 1, 2, 3, 4, 5, 6. Here you see clearly, since 1 belongs to A, since A is a subset of B, so 1 belongs to A, 1 also belongs to B. It means 2 belongs to A. It implies that 2 also belongs to B. 3 belongs to A. It implies that 3 also belongs to B. Here you see A is a subset of B. Why? Because all the elements of A are also the element in the set B. Okay, all the elements are contained in the set B, so B is the superset of A and A is the subset of B. So every element in A is an element of set B, so the set B is equal to superset of A. And this is the notation of the superset. Here you see the diagram, Venn diagram here. Look at here. Here the set A is oval shape. Yellow structure is inside the red structure, red oval shape. Here you clearly see here A is the subset of B, A is a part of B, and B is the superset of A. Right? A is the subset of B. Naturally in Odia we say A, B the opposite. B is the superset of A. In Odia you can say B, A the opposite. One Odia words I am just remember. Okay, look at your Venn diagram. Here is the set B, here is the set A. You see inside the set B, and what is the yellow structure, oval structure of A is there. So since B, it clear that B is A is contained in B, and all the elements of A are in B. So you see B is equal to 1, 2, 3, 4, these are the elements, suppose, and A is equal to 1, 2, then you see clearly B is a superset of A and A is a subset of B. Right? So one of the interesting Venn diagram. With the help of the Venn diagram also you can represent, you can clearly understand about the basic concept of the set theory. Venn diagram is the important part through the diagram, through the figure, and we can expand, okay, the basic concept of the set theory. We clearly understand the set A is a subset of set B from the Venn diagram. Right? Since a set is a well-defined collection of objects or elements grouped together within the basis, it can also be disintegrated into small set of its own called subset. Mathematically, a set A is referred to as the subset of another set B if every element of the set A is also an element of set B. Once again, to give the idea about the subset. Here is the subset. Once again, another interesting example. Consider a set A such that A is the set of all people living in your city Bhadrak. Another set B, the set of your family members. You see now, here B is the subset of A because each member of your family is also the resident of the city Bhadrak you live in. Every member, family members of your family, every family members, okay, are the part of the city Bhadrak because you are staying in Bhadrak. living in Bhadrak. So here B is a subset of A, and you see every element of the set B is a part of the numerous element belong to set A. Thus B is definitely a subset of A. Let's another set E is equal to set of all even numbers. To clear understanding about the subset, more example of the subset. Another set N is the set of all natural numbers. Clearly you see the set E is a subset of the set N, with all even natural numbers are contained in the set N, and all the elements of the set E are also the element of the set N, but all the elements of the set N are not the element of the set E. It means N contains E, but E does not contain N. That's why E is a subset of the natural number set of natural number N. Here is the Venn diagram. Look at here. Here is the set of natural number. Here is the set of even natural numbers. Clearly you see the yellow structure is inside the red structure, red oval structure. So clearly you can see, clear understanding, the E is a subset of N. Yes or no? The set E is a subset of set of natural number. Okay? Look at the Venn diagram. Right? I hope you will understand the concept about the idea of subset. Here N is a superset of E. If E is a subset of N, set E is a subset of N, then N is a superset of E. Right? Property of subset. It is interesting to note that every set is a subset of itself. A is a subset of A. Why? Because all elements of set are also in the set A. That's why every set is a subset of itself. Very important point. Every set is a subset of itself. Since empty set, null set or void set has no element, so the phi set is a subset of every set. If X belongs to A, that implies X belongs to B, then A is a subset of B. This is one of the important property also theorem. Here I am going to explain. If X belongs to A, even X is an element of A, then X is also an element in the set B, then A is a subset of B. This is the condition of the subset. If X is the element of the set A, then X is also the element of the set B, then A is a subset of B. The general formula, very interesting formula, the number of subsets of a given set A with n elements. Suppose a set has n elements, the total number of elements, very interesting formula, note down here, 2 to the power n, including the set A and the phi set. Right? So if A is equal to ABC, suppose the set A, 3 elements are there. So the cardinality of the set A is what? N of A is 3. So total number of subset including the set and phi is 2 to the power n, using the formula 2 to the power 3 is equal to 8. Understand? How many elements, how many subsets a set has, you can determine using the formula 2 to the power n. There is also an interesting derivation why the total number of subset of a given set is 2 to the power n. I will discuss in the next class. This is one of the very important theorem and which I will go and discuss. Superset. In mathematics, superset is a set contains all elements of another set. Once again, same thing I am going to discuss here to make you clarity about the subset and superset. We know that if B lies in A, then it means that A contains B. Yes or no? In other words, if B is a subset of A, then A is called what? Superset of B, naturally. More precisely, if set B is a subset of A, then A is also superset of B. Right? Look at here. Here is the set A. Here is set B. Here the A is the superset of B because all the elements of B are in the set A. Right? So you can write A is a subset of A is a superset of B because you see the oval structure, yellow structure A is, and red structure, red oval structure is inside the yellow structure. It means all the elements of B are in the set A, so A is a superset of B. Property of superset. Okay, note down here, every set is a superset of a null set or void set. It means A is a superset of phi, since phi has no elements. Since every set is a subset of itself, then every set is also a superset of itself. A is a superset of A. A is a superset of phi, right? Okay, here some example I have discussed here. Suppose if a set A is father, mother, brother, sister. This is a family. The set A is the family members. Okay, father, mother, brother, sister. Set B is the sister. Can you say how B is subset of A? Look at here. Because the set B, sister is a part of the family member. Yes or no? Right? The set A represents your family members and set B represents single element is your sister. And by the definition of subset, each element of the subset is included in the other set. Here all the elements of the set B are the element of the set A. And the element sister is a part of your family. That's why B is a subset of A. Once again, you see the Venn diagram. Clearly it has been, nicely it has been done. And this Venn diagram clearly shows that B is a subset of A. Right? Here the sister is a part of the family member. That's why the set B is a subset of set A. Right? Okay? Another question here I am discussing. The set A is equal to X such that X is an even natural number. The set B is equal to Y such that Y is a natural number. Determine who is the subset here. Look at here, diagram, Venn diagram. Yes, here the set A and the green part is set B, green oval structure. Clearly, the green oval structure is inside the yellow oval structure. It means all the elements of B are in set A. Okay, here the set A is 2, 4, 6, 8, etc. The set B is equal to 1, 2, 3, 4, up to etc. See clearly that all elements of the set A are included in the set B. So the set A is the the set B is the subset of A. Yes or no? The set A is the the set A is the subset of, here the set A is the subset of B. Look at here. Understand? Here this is the this will be really there is some good here, and this is the, you see, the set is even natural number, the set B is the natural number, so this set will be A. There is a mistaken in naming. Okay, right? And this set is B, this set is B. Can you change? Right? Here A is the subset of B. Because A is the set of even natural numbers and set A is the natural numbers. So all elements of the set A are in set B. That's why A is a subset of B. Once again check it, rectify the diagram in the naming. Okay? Understand? Clear? So you can cross this one you can cross. Right? Proper subset. Another important component. What is proper subset? A proper subset of a set is a subset of the set B if all the elements of the set A are in the set B, but at least one of the elements of the set B are not in the set A. It means that A and B are not equal. A is not equal to B. All the elements of A are in B, at least one of the element B are not in the set A. Then you can say A is a proper subset of B. Suppose for example, if A is equal to 1, 3, 5, the set B contains 1, 5. You see, here you see, what are you looking here? Here B is the subset of A, with all the elements of B are in A, because and A is the superset of B. Because why? The element 3 is not in the set B. That's why B is the proper subset. The proper set is also subset. Proper B is the proper subset of A. We can also say B is the subset of A. Every proper subset is a subset. But difference is that B is the proper subset of the set A. Very important point. Look up. Because the element 3, okay, are not in the set B. One of the element of the set A not in the set B. Here A is the superset of B. Okay, because 3 belongs to the set A, but 3 does not belong to the set B. So if one of the elements of A are not in the set B, then the set B is known as proper subset of the set A. Okay, don't confuse here. The proper subset is also subset, but the condition is that the old one, at least one of the element of the set A are not in the set B. Here you see 3 belongs to A, but 3 does not belongs to B. So B is a proper subset of the set A. Hence B is the proper subset of the set A. Right? What is the proper subset versus subset? And for subset, for two sets A and B, the set A is a subset of the set B. If every element in the set A is also in the set B, it is written as A is a subset of B. Proper subset for sets A and B, the set A is called proper subset of B if every element of the set A is also in the set B, but set A does not equal to the set B. And here A is a proper subset of the set B. And one of the element of the B are not in the set A. It means clear that in proper subset, two subsets are never equal. Okay? See, one of the set is A is a subset of B, A is also proper subset of B, and condition is that one of the element of the set B are not in the set A, is not in the set A. So, this is the condition, right? Understand? And A is a subset of B, A is also proper subset of B, every proper subset is also subset. The condition is that one of the element of the set B is not in the set A and two sets are unequal, right? Suppose if A is equal to ABC, then the number of proper subset of A is what? 2 to the power 3. How many proper subset is there? 2 to the power 3 minus 1, which is 8 minus 1, 7. Interesting point. Total number of proper subset of A, 2 to the power 3 minus 1, which is 7. Total number of subset what? 2 to the power 3. Total number of proper subset is 2 to the power 3 minus 1, which is 8 minus 1, 7. This is another formula. Important points. How to find total number of proper subset. This is clearly the differences between the proper subset and subset. Okay? Another important point is equal sets. If two sets have same element in them, then they are called equal sets. For example, suppose the set A is 1, 2, 3 and the set B is how many elements? Also 1, 2, 3. Clearly see that every element of the set A are in the set B and every element of the set B are also elements set A. In this case we can say yes, the set A and set B are equal sets. And if the two sets are equal, we can represent it clearly by giving the equal sign. A is equal to B. If two sets are equal, then their cardinality of the set is always same. The element will be same and their cardinality will be also same. Note down here. Okay? It is one of the important theorem of equal sets. Let us see, if A is a subset of B and B is a subset of A, then prove that A equal to B. This is one of the important points, theorem. Simple theorem for you. And given that A is a subset of B, as per the definition, since A is a subset of B, suppose if X belongs to A, then X belongs to B. Yes or no? Because A is a subset of B. Yes or no? Right? Similarly, every element of the set A are the element of the set B, it is clearly understood because A is a subset of B. And again given that B is a subset of A. Since B is a subset of A, if X belongs to B, suppose X is an element of the set B, then is also element of the set A. X is also element of the set A. It means if X belongs to B, then X belongs to also A, as per the definition, because B is a subset of A. With all the element of the set B are also the element of the set A. It means every element of the set B are also the element of the set A. So from these 2 points, it is clearly understood that the two sets are equal. A is equal to B. So condition, remember students, and if A is a subset of B and B is a subset of A, then prove that A equal to B, two sets are equal. This is one of the important theorem and property of the equal sets. Note down. And this will be helpful in proving the various statement while we are discussing the set operation. While proving the various statement of set operation. De Morgan's law, suppose. So many mathematical set theory operation we have to discuss, and we have to verify the statement, we have to prove the statement, and this concept most useful. If A is a subset of B and B is a subset of A, then A equal to B. Understand? Right? Note down. Let's see. Proceed. Another concept, that is the unequal sets. If two sets have at least one different element, then they are unequal sets. Suppose the set A is equal to 1, 2, 3 and the set B is 2, 3, 4. You see, here 4 is an element in the set B, but 4 is not an element in the set A. That's why both sets are unequal. A is not equal to B. And you can write, okay, A is not equal to B by giving not equal to sign. Right? Understand? Very simple definition concept. This is one of the important and vital concept, equivalent set. Equivalent set, one of the vital concept of the set theory. Okay, let's see. Two sets A and B are said to be equivalent if they have the same cardinality. It means the number of elements of the set A is equal to the number of elements in the set B, then the two sets are said to be equivalent set. In general, we can say two sets are equivalent to each other if the number of elements in both the sets are equal. And it is not necessary that they are the same element or they are a subset to each other. Okay, the cardinality of the set must be equal. Their element may be differ or may be same, but if the total number of elements of one set A is equal to the total number of elements in the set B, another set B, then the both sets are said to be equivalent set. In equivalent set, their number of elements must be equal. Equivalent set are represented by an equivalent sign, okay, just by similarity symbol and congruence symbol. One example is there. Suppose A is equal to 1, 2, 3, 4, B is equal to A, B, C, D. Two sets are here. Can you see the number of elements of the set A, which is 4, and number of elements of the set B, which is also 4. You see the number of elements of the set A is equal to number of elements of the set B. It means n of A is equal to n of B is equal to 4. They have the same cardinality. That's why the set A and B are said to be equal set. Equivalent set. The set A equivalent to set B. And this is the sign to represent the equivalent sets. Right? Here is the Venn diagram of the equivalent set. Interesting diagram. Okay. Here is the set A. Here is another set B. Okay. And here one is an element of the set A, and which corresponds to another element of the set B. Here is another element 2 of the set A, who is correspond to the set B. Here 3 corresponds to the element C of the set B. Okay. And the element 4 of the set A correspond to the set element D of the set B. It means you see that an interesting observation we are finding for, okay, it's made for every unique element in the set A, there is an unique element is assigned with an unique element in the set B. This is the most important observation and condition that the set are equivalent set. It means the number of elements of the set A are equal to number of elements of the set B. Here the sets elements are different. You see, the set element of set A and B are different, but there is every unique element in the set A is assigned with an unique element in the set B. So in this case we can say, okay, the A equivalent to B, right? And the two equivalent sets have one correspondence. One important property, two infinite sets are equivalent set. Although you cannot determine their cardinality, because if they have one correspondence between them, even they have the same or different elements. It means that every unique element of the first set corresponds to every unique element of the other set. Suppose the set M is the cube of natural numbers, another set is the set of natural numbers. You look at here, every element in the set M is assigned to a unique element in the set N. Look at here, look at here, look at here. Here 5 is assigned to 5 cube. Yes, so every unique element is assigned to the unique element in the set N. We can say the set M is equal to the set N. Okay, even the two infinite sets are said to be equivalent. Equivalent set को in ODI we say sadrusha set, right? M equivalent to N, right? Understand? Relation between the equivalent set and equivalent set. Two sets are equal if they have exactly the same element. If their elements and the number of elements both are same, without any order and repetition of element. Already know, two equal sets, the elements should be same. Naturally, the element number of elements should be same. But in equivalent set, the number of elements are always same. But the elements can be same or different. But the number of elements should be same. This is the condition, relationship between the equal set and equivalent set. In equal set, the elements are same and their numbers are same. In equivalent set, the numbers are same, the element may be same or may be different. So one of the important common property between the equal set and equivalent set, the number of element in equal set and equivalent set are same, right? Understand? But what is the difference? In equivalent set, the elements may be same, may be different, but in equal set, the element must be same element. In equal set, elements should be same. So equal sets are equivalent set. Every equal sets are equivalent set. These are the property of the equivalent set and equivalent set. Relationship between equal set and equivalent set. Right? Classify the following the sets as equivalent set or equal set. Suppose the set A, it contains a set of vowels in the English alphabet. Set B, it contains a set of all the letters in the word vowel. Another problem I have given, the set B is X such that X is a letter in the word life, and another set A is the element F-I-L-F. Now let's see the solution. The contents, consider the set A and B. Here A is the alphabet's vowels, A, E, I, O, U. And the set B, V, O, W, E, L. Look at here. Here the number of element of the set A is 5 and the number of element in the set B is also 5. Since the number of element A is equal to number of element set B, so they are equivalent set. And again you see, their elements are also same. The set A and B are also equal. Yes or no? Their equivalent set are also equal set. But this set you see, the life E, L, I, F, E. Right? Another set F, I, L, E. Do you see here? In both the sets we have the same elements, hence they are equal sets. Yes or no? Yes? Right? And all elements of the set E and F are same. Because you see the element L, also the element of the set E and also the element of the set F. And I is an element of the set B, also element of the set B. And F belongs to E, also F belongs to E. So they are equal set as well as the equivalent set. Right? Okay. Another point, overlapping sets. Two sets are said to be overlapping if at least one element from the set A is present in the set B. For example, the set A is equal to 2, 4, 6 and the set B is equal to 4, 8, 6. 4, 8, 10. Two sets are there and you see the element 4 is present in the set A as well as in the set B. Here 4 is an element of the set A, right? Here 4 is an element of the set A, now element of the set B, right? Okay. Right? So if the both elements are both sets are common element, here 4 is the common element. If the two sets have a common element, they are said to be the then the sets are said to be overlapping sets. A and B are overlapping sets if they have any common element, right? Understand? Yes, here 4 is an element of the set A and 4 is an element of the set B. So since 4 is the common element of both the set A and B, so A and B are said to be overlapping set, right? Look at the Venn diagram here, overlapping sets. Okay, here 4 is the element, you see 4 is the element, common element in the common area, intersecting area. Okay, so both the sets are said to be, the set A and B are said to be what? Overlapping sets. Clear? Yes. Disjoint sets, non-overlapping sets. In the two sets are said to be disjoint set if there are no common element in both the sets. For example, the set A is 1, 2, 3, 4 and the set B is equal to 5, 6, 7, 8. You see, is there any common element? No element in the set A are in B and no element in the set B are in A. Okay, so both the sets are said to be disjoint sets and non-overlapping sets. Two disjoint sets have no common element, no doubt. Here is the diagram, Venn diagram for you. Look at here. Suppose the set 1, 2, 3, 4 it contains. Another set contains 6, 5, 7, 8. See, the set A and B are non-overlapping set or disjoint set, and disjoint set they never intersect, right? And having no common element. So if the sets having no common element are said to be disjoint sets. If the set having common element are said to be overlapping sets. Another important definition of the set, that is the universal set. A universal set is a collection of all elements or members of all the related sets, known as its subset. Under our consideration, if number of sets are the subset of a given particular set, then the set is known as, the given set is known as universal set. Okay. For example, the universal set is the set of all the people in the world. The set of all the people in the world. The set of all the people in each country can be considered a subset of the universal set. All the people of India is a part of the world. So India is a subset of the universe world. Okay. Similarly, if all the stars in a Milky Way galaxy, another interesting example, okay, of universal set. All the stars in a Milky Way galaxy is a nice example of the universal set if we consider all the stars in a Milky Way galaxy. The set of all students of a school is universal set. If we consider the set of different students of different classes reading in the same school. Students of different classes, if you take the student of different classes by taking the set, and they must be the student of same schools. The set of all people living in different states in India are subsets of our country in India. It means if you consider the different states, number of states, and all the sets are the subset of a given particular set, then such kind of set is said to be universal set. The set of people living in different state is a part of our country. Thus our country is what type of set? Universal set. Thus the set of people in India is universal set. The universal set is denoted by letter capital U and is a set containing all the elements of all its subset. See an interesting example for you here. Let's consider an example with the three sets A, B, C are given, and A is a set elements 2, 4, 6, and B is an element 1, 3, 7, 9, 11. C is a set 4, 8, 11. Can you make an universal set? We need to find the universal set of all the sets A, B, C. So all the elements of a given set are contained in the universal set as per the definition. So the universal set U of the set ABC is equal to 1, 2, 3, 4, 6, 7, 8, 9, 11. And clearly see the set A is all the elements of the set A are in the set U, universal set. So A is a subset of U. Similarly B is a subset of U and C is a subset of the universal set U. It means all the sets under consideration are the subset of a particular set, then the set U, that particular set, given set, is known as universal set. Right? Here is another example, interesting example for you. Consider that there are three sets, namely X, Y, Z. The element of each sets are given below. The element, okay, here the element, the set Y contain the element. Look at the elements of the set X, Y, Z. Find the universal set of this set X, Y, Z. Look at here. We know that the universal set contains all elements of the given set and the subset of the universal set. The set X must be a subset of universal set U. The set Y must be a subset of universal set what? U, and the set Z must be a subset of universal set U. Right? So you have to write the universal set. We can write it as, okay, here the elements of the universal set, and clearly you see all the elements of the universal set, okay, contain all the elements of the set X, Y, Z, and all the elements of the X are in the set U. So X is a subset of U. Similarly, all the elements of the set Y are the element of the set U. So the Y is a subset of U. Similarly, Z is a subset of U. So understand? So these are the all sets are subset of U. That's why under consideration if number of sets are the subset of a given particular set, then that set is known as universal set. The universal set contains all the elements of the different sets. Then you can say that is an universal set. Right? Here is the universal set diagram. I am doing Venn diagram, rectangular shape. See here, look at here. Okay, here the set X, here the set Y, here the set Z, here the set, okay, you see here, look at here, look at here. Clearly see the X and Z are overlapping set. X and Z, what are the common element? The common element you see clearly of the set is what? Here 4 is an element of the set A, also 4 is an element of set Z. Similarly, the 8 is an element of the set X and 8 is also element of the set Z. That's why you see here written 8 and 4 are overlapping elements, common element of the set X and Z. Similarly, if you see set Y and Z, and here 11 is an element of the set Y, 11 is also element of the set Z. Here Z and Y are overlapping set 11. Understand? Okay. Is it clear? So these are the example of universal set. Here universal set can be written as, okay, by taking all the elements of the set X, Y, Z. The universal set contains all the elements of the different sets. The set U contains all the elements of the set X. The set U contains all the elements of the set Y. The set U contains all the elements of the set Z. That's why U is an universal set. Is it clear about the universal set? Another interesting example. The set A is the set of all the people of Odisha. The set B is the set of all peoples in Bihar. the set C is the all people of Rajasthan, the set D is the set the all people of Kerala, then E the set of population of India. You can clearly understand the universal set. Look at the Venn diagram here. Yes, this is set A, Odisha. Okay, understand? Look at the Venn diagram here. Okay, right? Once again see, right? How to represent universal set, and here is the universal set here. Here is the universal set. And universal set must be represented by the rectangle, okay, and their subset are represented by the oval structure, right? Look at here. Another important point is the power set. One of the most important point of the concept of the set theory is the power set. How to find the power set? Let's see. A power set is defined as the set of all the subset of any given set, including the empty set and the set itself also. The power set of the set A is denoted by the notation P of A, if A is the given set. A power set can be imagined as a place holder of all subset of a given set. So if the set is given, we have to find out number of subset, and all the subset can be taken as an element. I have to write in another set. That set is known as power set. In other words, the subset of the sets are the members of the element of a power set. Suppose the set is given, and we have to write all the subset of a given set, and all the subset of given set are taken as the element of another set, and that resulting set is known as the power set. The number of elements of the power set is given by 2 to the power n, already it is discussed, which include the phi set and the set itself. The number of elements of the power set is 2 to the power n. Note down the formula. Suppose if A is equal to the set is an age set and contains element AB, then write the power set of A. Clearly you see the coordinate of the set A, number of element, how many elements it has? N is equal to, it has 2 elements. The total number of subset of A is equal to 2 to the power n, which is 4. So it has 4 elements. If A has contains 2 elements, total number of subset has 4 elements. Total number of subset will be 4. It has 4 subset, and all the subsets of A are: first subset of phi is a subset of A, second A is a subset of A, because every subset is a subset of, every set is a subset of itself, and first point, every null set is a subset of given set. Here every set is a subset of itself. Here if you write the element A as in the form of set, is also a subset of the set A. Similarly, here you take the B as the element and write the B in the form of set by giving curly brackets, and you see this, it becomes set which is a subset of the set A. There the power set, by taking all the subset in a given set, okay, as element. See, all the elements are written as element and have included the curly bracket, so it becomes set, and that set is known as nothing known as power set. So the power set of A is P of A is equal to phi A, okay, set A and set B. Right? Understand? Look at once again here how to find the power set of the set A by taking all the subset of a given set. Write the power set of the set S. Here the set S is equal to 1, 2, 3. The coordinate of the set S is equal to n of S is equal to 3. It has 3 elements. So total number of subset of the set S, which is 2 to the power n, which is 8. It has 8 subsets. The total number of elements in the power set is also 8, because the total number of elements, total number of subset of the set A are also the same as the number of element of the power set of the set S. All the subset of S are, first you see, first subset what? Phi is a subset of the set S, because the empty set is a subset of every set. Here S is a subset of S, every set is a subset of itself. Here the set 1 is a subset of S, the set 2 is a subset of S, and the set 3 is a subset of S. So you are getting here Here another point you see subset 1 and 2. You take 1 and 2 here. By taking 1 and 2 as the element in the form of set is also subset of S. Similarly, the taking the element 1 and 3 as the here and as set and is also subset of S. Similarly, here the element 3 and 2 and 3 taken as written in the form of set with the curly bracket is also subset of the set S. Right? Okay, so we have to write all the power set we can write by taking all the subset as element. Here 5, the set 1, 2, 3, the set 1, set 2, set 3, set 1, 2, set 1, 3, set 2, 3. So these are the power set. So you can find out the power set by taking all the elements, okay, by taking all the subsets of a given set. Okay, understand? Here is another question, very interesting question, most vital question. Okay, so that the n of p of phi is equal to 4. The number of power set of power set of power set of phi set is 4. How? You see, we know that the phi set is no element. A number of element in the phi set is 0. So the power set has one element. So it has so the power set has one element, which is power of phi. Okay, the p of phi is phi, which is an element of the set. Again, you see, if you take the power of power set of phi, you see it has one element, so number of subset will be 2 to the power 1, which is 2 to the power 0. So it has one element, 2 to the power 1 is how much? 2. So the power set of p of phi is phi and another set phi. Clear? And again, you see it has how many elements? 2 elements. So number of element of the p of phi, which is also 2. It has 2 elements, so you can say total number of subset 2 to the power n, which is 2 to the power 2, which is 4. Clear? Understand? So number of proper subset of p of phi, which is how many elements you see? 1, 2, 3, 4. 5 set phi, you see these are the phi sets. So it has total number of element number of element of p of phi, which is 4. Clear? So here is an assignment for you. These are the most vital questions I have discussed for you. Most vital concept has been discussed to you, and it covers all the basic concept. Definition of the types of set has been vividly described. I'll be thankful to you for your patience and eagerness. Once again, thank you for your interest and eagerness. Let us go once again and again. Okay, the basic concept set theory are most vital. And then in next class we shall discuss the set operation and application of the set theory in solving the various problems. With this, thank you for your once again. Thank you for your patience, interest and eagerness for the class.
Once again, welcome back with another vital and important class which I am going to discuss here, okay, of your class 11 mathematics based on the concept of set theory. And dear students, all of you know in the previous class we have already discussed the introduction set theory and the types of set theory. Vividly, an entire concept has been discussed, and in this class I am going to explain some of the important statement, vital statement, and also some problem which are most useful to you, okay, for the different kind of exam and competitive exam which I am going to discuss here. Okay, I hope it will help you and guide you in solving the different kind of problem. Okay, and here is the concept I am going to discuss. Look at the concept, which topic I am going to discuss here. Here is a topic, okay, important statement that I am going to prove that the total number of subset having n elements is 2 to the power n. Okay, understand? Another concept here which I am going to discuss here. Look at here, two finite sets having x and y element. The total number of subset of the first set is 56 more than the total number of elements of the second set. Find the value of x and y. One of the interesting problem which I am going to explain of your class 11 mathematics. Also you can find in different kind of competitive exam. One of the interesting problem. Another concept
which I am going to discuss. Yes, the cardinality of power set of power set of power set of power set of null set is equal to 16. Right? Okay. Here is another simple fundamental concept I am discussing in one class for you. Okay. How many elements of the power set of X has if the X is null set? Another simple and fundamental problem. Okay. Another interesting problem which I am going to discuss vividly for you. Okay. Yes. What is the total number of possible proper subset of a set having n elements? So these are the so many questions I am going to discuss. Most important problem. I hope it will help you. Okay, and also you will find interest in learning this problem. Okay, and these problems are mostly useful to you. Right? Let's see of your class 11 mathematics based on the concept of set theory, which I am going to discuss. Okay, and do you know, students, how many subset a set has? Okay, let's see how. The total number of subset having n elements is 2 to the power n. Understand? Okay. Total number of subset of any finite set having n element is 2 to the power n. Understand? So here I am going to discuss. This is really an interesting statement to be proved. Okay, which is mostly applicable in solving the various problems. Let's see how. Okay. Understand? So let A be finite set. Let us suppose the set A has no element. It can return, okay, as A is equal to null set because of no element. Thus the cardinality of the set A, which is n of A, is 0 because of no element. Since we know that every set is a subset of itself, so its power set of A is written as, okay, null set, including here the null set has been written including the curly bracket. And student know whatever written within the curly bracket is an element. So here phi is an element. So the power set of A has one element. So the total number of elements of the power set of A, which is n of PA, is 1. Okay. Thus you get that when the set A has no element, it means number of element is 0. Then the total number of subset of the power set is what? 1. And we can write 1 means what? 2 to the power 0, because the value of 2 to the power 0 is 1. Thus when a set has no element, when n is equal to 0, the power set, total number of subset or the total number of element in the power set is 2 to the power 0. Right? Understand? Okay. Suppose the set has one element. Let the A be a set having element x. X is an element of the set S. So the cardinality of the set A, which is n of h1, yes or no? So its total number of subset. What are the subset are there? You are able to see these are the subset of the set A. Hence, if you write in the power set, and you know all the subset can be written in the as element, and that set resulting set will be power set. So the power set of A, by taking all the subset of A, which is shown, and you can see this is the power set of the power set of A, and clearly you see when the cardinality of the set A is 1, so the cardinality of the power set is 2, and you can write 2 to the power 1, yes or no? 2, and yes, thus when a set has one element and the total number of elements in the power set or total number of subset of the set A is 2 to the power 1. Okay, understand? So similarly, let us suppose the set has two elements. Let A be a set having element x and y. So the cardinality of the set A is what? N of A is 2, right? How many elements are there? 2 elements. The total number of subset, these are the subset of the set A. How many subsets are there? There are 4 subsets. So we can write in the power set as P of A, okay, can be taken, these subsets are taken as the element, and we can write the power set of A. And the cardinality of the power set of A, how many elements? If you count, okay, if you count, you see, yes, understand? So here the power set of A is 1, 2, 3, 4. So the cardinality of the power set has how many elements? 4 elements. And we can write also, yes, 4 can be written 2 to the power cardinality of the set A. And you clearly see, tell me what is the cardinality of set A? Is 2. The cardinality of the set is 2. That's why, so the the number of element of the power set and which is equal to 2 to the power coordinate of the set A. There is a relationship between the coordinate of the number of element of the set A and its and the power of 2. You see clearly? Okay, understand? So if you write which is 2 to the power 2, which is what? 4. Thus it is clear that when a set has 2 elements, its total number of power set or it's the total number of subset of that set is 2 to the power 2. And you see clearly, you can see the number of element of a set and here the power. Are you able to see? There is a beautiful relationship between the number of element and the power of 2. Okay, similarly, suppose the set, so it is clear that when n is equal to 0, the total number of subset, what? 1, yes or no? Which is 2 to the power 0, right? Thus, when the set has 1 element, its total number of power set is 2 to the power 1, right? Similarly, okay, when a set has 3 elements, can you say the total number of subset? Or we can write the cardinal of the power of set. The cardinality of the power set of A, which is 2 to the power 3. Look at here. Here how many elements? 3 elements. Here the power of 2 is 3. Understand? So the cardinality of the power set is 2 to the power 3. Similarly, when a set has 4 elements, tell me total number of subset is the cardinality of the power of set, which is 2 to the power 4. When a set has 5 elements, its total number of subset, okay, the cardinality of the power set of A, the cardinality of the power set of A, which is 2 to the power 5. In the same process, if you continue, and when a set has R element, can you say what is the total number of subset and what is the power set of cardinality of the power set of A, which is 2 to the power R? Clearly understood? Thus, it is understood that when a set has n element, its total number of subset is the cardinality of the power set of A, which is 2 to the power n. Understand? Okay? Thus, and it is clearly understood that, okay, that number of subset of any finite sets having n elements is always 2 to the power n, and this is one of the important statement and property of any finite set. How to find out the total number of subset and how many subsets finite set has, you can clearly determine. Then it will be easy for you that what are the subsets are there. Yes, if you know the total number of subset of any finite sets, then you can find out what are the subset of any finite set of the set has. Okay, can be determined. This is one of the interesting problem for you. Okay, understand? I hope you have understood it. Let us come to the next question here. Another concept, interesting concept, which I am going to discuss. Two finite sets having x and y element, the total number of subset of the set of the first set is 56 more than the total number of element of the second set. Find the value of x and y. One of the interesting, amazing concept. Okay, based on the concept of set theory, most will find in different kind of competitive exam. Look at here. Okay, let the two finite sets be A and B. Understand? So the set A has x element and the set B has y element. So the number of subset of the set A is 2 to the power x according to the formula, because the number of element of the set A is x. Similarly, the set B has the y element, so the total number of subset of the set B is 2 to the power y. Understand? Yes. But according to the question, it is given that the total number of subset of the first set is 56 more than the total number of subset of the second set. Yes or no? Yes. So using this condition, and we can use 2 to the power x minus 2 to the power y is equal to 56. The difference between the total number of subset of the set A and B is 56. Thus, 2 to the power x minus 2 to the power y is equal to 56. Now just you simplify and modify the statement. Multiply 2 to the power y divided 2 to the power y in the LHS. Look at here. Okay, and here 2 to the power y by 2 to the power y has been multiplied to LHS. Okay, just you have to modify the statement. And 2 to the power y whole into 2 to the power x minus 2 to the power y divided by 2 to the power y, which is 56 can be written 8 multiplied 7 because 8 7s are 56, right? So here 2 to the power y whole into 2 to the power x divided by 2 to the power y minus 2 to the power y divided by 2 to the power y is equal to 8 whole into 8 minus 1. 7 can be written 8 minus 1. You just modify the statement Okay. Now 2 to the power y whole into 2 to the power x divided by 2 to the power y, which is, what is the formula? Can you tell me? 2 to the power x minus y, and you can cancel here. You see the 2 to the power y and 2 to the power y will be cancelled. The value will be 1. Understand? Thus 2 to the power y whole into 2 to the power x minus y minus 1, and 8 can be written in the form of exponent 2 to the power 3 whole into 2 to the power 3 minus 1. Okay. Thus we get 2 to the power y whole into 2 to the power x minus y minus 1 is equal to 2 to the power 3 whole into 2 to the power 3 minus 1. Okay. Understand? And if you compare on both sides, you see here clearly, here the power of 2 is y, here the power of 2 is what? 3. So we will compare this power. Okay. Look at here. Understand? And we can compare y is equal to 3. Similarly, here you see, here the power of 2 is here x minus y, and here a power is what? 2 is 3. So we will compare this one. Okay. And you see x minus y is equal to 3. Thus y is equal to 3 and x minus y is equal to 3, and comparing both sides we shall get, right? And x minus y is equal to 3. By putting the values of y, we shall get x is equal to 3 plus 3, which is x is equal to 6. Thus we get that x is equal to 6, the value of x is equal to 6, and the value of y is equal to 3. Understand? This is one of the interesting problem. Okay, and I hope and we will follow the question. Okay, let us come to the next problem here. Another interesting statement we are going to prove. The cardinality of the power set of null set is 16. Okay, let's see. And we know that phi set is null set. Yes, and which does not have any element, and the number of elements of the set is what? 0. The cardinality of the phi set is 0, right? And the power set has one element. Hence, the power set of the null set P of phi is equal to phi. Okay, how many elements? One element. Again, you find the power set of phi. How many? 2 elements. Clearly understood that. And the cardinality of the power set of phi, which is 2 elements. Yes or no? Thus, the total number of subset of the cardinality of the power set of phi, which is 2 to the power n, which is 2 to the power 2, which is what? 4. Thus, the power set of the cardinality of the power set of null set is 4. Right? Understand? So, look at here. Again, the power set. Thus, we get that if you write the power set of the power set, you see P of phi. What are the elements are there? 4 elements are there. Yes, and hence the cardinality is what? 4. Thus, it is clearly understood that the cardinality of the power set of phi set is 4. Understood? Yes. Okay. Again, you see. Again, you will find out the power set of this set. Let us. Okay. And because this is the, understand, the cardinal of this set is 4, and again you can find out what is the total number of subset of this. Okay. And power set of phi, we can write 2 to the power n, because the number of elements is what? How many elements are there? 4 elements. So the total number of subset of the power set of null set, which is 2 to the power n as per the formula, and here the value of n is what? 4. Okay, and by putting the value we shall get 2 to the power 4, which is 16. One of the interesting problem. Thus we get that the cardinality of the power set is of the null set is equal to 16. Most of the interesting problem it is, and you will find the different kind of competitive exam. Okay, is it clear all of you? I hope you will understand, and is a question I am giving you. Okay, and this question you have to try. Yes, look at this, the question here. So I hope and you will answer this question, and you will send me to me in my description box. Okay, let's see. I hope and you can do this problem. Understand? Once again have a look, right, and try for yourself. Understand? Okay. Let us have another problem. Simple and fundamental problem. Same problem we discuss. What is the total number of possible proper subset of a set having n elements? It is one of the interesting problem. How many total number of possible proper subset you have to find out of any finite set? Yes? Understand? So, the total number of possible proper subset of any finite sets having n elements is 2 to the power n minus 1. Note down this formula. Yes, the total number of possible proper subset of any finite sets having n element is 2 to the power n minus 1. Understand? Okay. So, let's see how. Suppose the set has 3 elements. So, its proper subset. What is the proper subset? Here the proper set of the set of A, we can write all the proper set. We know all the subset of all the subset. Let's write what are the proper subset. You see, here the proper subset are, okay, how many proper, so what are the elements? What are the elements are there and how many elements are there? It is clearly understood. You can see clearly, okay, in the box, in the screen, look at here, how many proper subset are there? Here 1, 2, 3, 4, 5, 6, 7. How many proper subset? It has 7 subset. It means if the set A has 3 elements, it has 7 proper subset. Total number of proper subset what? 7. Understand? So in proper, and all of you know the proper subset. Okay. You see, while you are finding the sets, total number of subset. Total number of subset how many? 2 to the power n, which should be 8 here, and all subset are here. Only the set A is not here. While you are considering calculating the total number of proper subset, remember the student, the set A should not be taken as a proper subset because any set is not a proper subset of itself. This is one of the vital definition of the proper subset. Any set is not a proper subset of itself. So the total number of possible proper subset is equal to n of A, which is 7. Understand? Okay, here is written, you see the proper subset. The set A cannot be the proper subset of itself. This is one of the definition and fundamental definition of the proper subset. Any set cannot be the proper subset of itself. That's why while you are finding the proper subset, and there are 7 proper subsets you have taken, the set A has not been taken as a proper subset. So the total number of proper subset of A is n of A 7. And you can write 7 is equal to 8 minus 1, yes or no? And 8 can be written 2 cube minus 1. And you clearly see, here you see, how many elements you see here? The set has 3 elements, and you see the power of 2 is also 3. And difference minus 1. Minus 1 means we have to exclude the set A as a proper subset. That's why we have to do minus 1. Thus the total number of proper subset of the set A, which is n of A, which is 2 to the power 3 minus 1. If you take in place of 3 is n generally, so you can derive the general formula. The total number of proper subset is 2 to the power n minus 1. Is it clear? Understand? And similarly, you can find out the total number of proper subset of any set having n elements is 2 to the power n minus 1. This is one of the interesting and problem, and also, and it will you can get it in different kind of exam. So this formula, try to remember, understand, and use it, and whenever we are facing such kind of problem. Okay, understand? So let's see. Is another fundamental problem. Okay, I am discussing how many elements the power set of X has if X is an null set. Already know a null set means what? Okay, no element. And we know that if a set with n element, then total number of kernel of set is n. Yes? Yes or no? We know that if a set with n elements, then the cardinality of the set is n, and its the kernel of the power set is 2 to the power n. Already discussed in the question number 1, first problem, first statement we prove. Yes, and here given that X is a null set, it does not mean it has no element. So the cardinality of the set X is n is equal to 0 because it has no element, and the cardinal of power set using the formula 2 to the power n, simply just in place of n you write 0. Yes, so 2 to the power 0 is what? 1. Thus the total number of power set, yes, the cardinal of the power set is 1. Hence, okay, the power set of X has 1 element. Understand? Okay. This is just a simple problem based on the using the formula, okay, 2 to the power n. The total number of proper subset of set is 2 to the power n. Okay, so how you see the formula can be useful in solving, in finding the total number of subset, okay, of a given set, or you can find out the cardinality, the power set of A. Yes, understand? So the power set of A is Px has one element, understand? So these are the most vital problem. Okay, here I have discussed vividly for you. I hope and you will follow on the class. Yes, and also practice the similar kind of problem. Okay, here is an assignment for you. Look at the assignment. Simple concept based on the concept of subset, which you already know, and you can do it. Okay, so it is my great pleasure to explain such kind of problem to you. I hope you will follow the class. Okay, thank you for your interest and eagerness for the class. I hope the class will be most beneficial to you. Yes, once again, thank you for your interest and eagerness for the class. Thank you, student.